We are continuing our work with polynomial functions, and today we're going to use what we know about factors and remainders, and we're going to learn about the factor theorem and the remainder theorem as a way to deepen our understanding. So just refreshing your memory on factors. We know that a number can be broken up into factors. So for example, the number 42, we can write it as 2 times 3 times 7, where 2, 3, and 7 are all factors of the number 42. Now the polynomial example, I have taken the x squared minus 6x plus 5, and I've broken it up into 2 linear binomial factors, and I used backwards FOIL. And remember, we can check that the first 2 multiplied together is my x squared. Then I can look at my outside 2 and my inside 2. That's negative 1x minus 5x is negative 6x. And then the last 2 multiplied together is positive 5. So when it comes to polynomials, we can also break it up into factors. 2 polynomials which multiply together to equal the polynomial. In this screen, we're asked to determine the zeros of each function. And what I noticed immediately in the first example is that there is a 2 that's common to all 3 terms, and there is an x that's common to all 3 terms. So I factored out what I'm going to call the greatest common factor of 2x, leaving me with a quadratic trinomial, x squared plus 5x plus 6. And then I looked at that trinomial and said, oh, I can break that up into 2 binomial factors. And I end up rewriting my original function as 2x times x plus 3 times x plus 2. And I can set each one of these pieces to 0, giving me my zeros of 0, negative 3, and negative 2. And so I'm just using what I know about factoring. I'm using what I know about the zero product property. And I'm realizing that this cubic polynomial function passes through the x-axis at 0, negative 3, and negative 2. And these are what we call single roots. So in the next example, I see that there's a 3 that's common to all 3 terms, a factor of 3, and there's an x that they all have. So I factored out that 3x, leaving me with x squared minus x minus 12, which is, again, a quadratic trinomial that can be factored using reverse FOIL. So I've done that. And this time when I wrote my zeros, right, determining the zeros of each function, I wrote it in set notation form. There are 3 zeros of this function. And the 3 places that this function passes through the x-axis are negative 3, 0, and 4. So that's not overly new. That's just taking what you already knew about factoring and bringing it into polynomials. The factor theorem says that the expression x minus a is a factor of a polynomial if and only if the value of a is a 0 of the related polynomial function. Okay, so if this number that follows the minus sign is a 0, then x minus a is a factor. All right, let's kind of keep that in mind here. So we're asked to write a function in standard form, and we're given 3 roots, one of which is what we call a double root, right? And so using the factor theorem from the previous slide, I'm writing my factors as x minus this number times x minus that number times x minus that number. And I'm just going to fix up my factored form here. Minus and negative is plus, and x minus 3, I'm going to square that because that term appears twice. So would this, if I knew what the roots are, and I can now write the equation, would I be able to sketch this graph? Well, sure, because you have experienced sketching a function, right? You know that this is a third degree. You know the leading coefficient is 1, so the right end goes up, the left end goes down. You know there's a double root at 3 and there's a single root at -2. So keep all that in mind. Here, I'm going to apply my factor theorem. And each one of these 4 zeros, I'm going to write my factors as x minus this 0, which is just x, times x minus 1, times x minus 2, x minus 3. So here is my factored form of my polynomial function. But it says to write each one in standard form. So this is where we have to use what we know about algebraic manipulation, right? And so I think what I'll do is I'll start over here. And should I start here? Why not? And I will I distribute the x into both terms here in this binomial, and I get f of x is equal to, this is going to be x squared minus x, right? Now that's going to be in parentheses because I've just distributed my x here and here. Now these two binomials, I'm going to FOIL them out, and I'm going to get x squared. I'm going to do minus 3x minus 2x, right? That's minus 5x. And -2 times -3 is positive 6. Now what I want to do is I want to do double distributive. Take the x squared and multiply it to all 3 terms. So that's going to be x to the 4th. This is going to be minus 5x cubed. This is going to be plus 6x squared. I think I have to shrink this down to fit everything on. So then I have my minus x, which I'm going to be distributing to all 3 terms. So it's going to be minus x cubed. And then negative x times negative 5x is plus 5x squared. Negative x times positive 6 is negative 6x. So I did what's called the double distributive there. I could have used the box, okay, but I did double distributive. Now I'm going to combine my like terms. F of x equals, there's 1 x to the 4th term. So this is going to be a 4th degree polynomial function, which makes sense because there's 4 roots. X cubed terms, let's combine them. Negative 5x cubed minus x cubed is negative 6x cubed. How about the x squared terms? Positive 11x squared. The linear terms, there's just the minus 6x. I'm looking for constant terms, and I don't see any constant terms. So I think that we've simplified it correctly. X to the 4th, I'm just checking, minus 6x cubed plus 11x squared minus 6x. Okay, great. Now what we can do is we can take this factored form into Desmos. X times x minus 1 x times x minus 1 times x minus 2 times x minus 3. It looks like this, and to prove that we did this correctly, I can just copy and paste this right into Desmos. And look, it worked perfectly. See how it graphed it right on top of the existing function? That tells you that I multiplied correctly. This is called standard form. It's standard form because it's the highest degree comes first and then descending order. And so what I want you to do is to multiply this one out into standard form and make sure, using Desmos, that your multiplication, that your standard form is correct. All right, I'm going to put this on pause here, and we'll complete the rest of it in part 3.